Factoring, an overview. So we'll do a few examples of each style of basic factoring. The first style is common factoring. And in this case, we're looking at the two terms and we're trying to find the biggest number and the smallest common variable. It's actually the largest common variable, but when we do it, you'll find out what I mean by the smallest. So in this case, when you look at the numbers, 6 and 3, 3 is the largest common number. When you look at the variables, you've got an a squared and an a, remembering that there's an invisible 1 above that a. So we have two a's here and one a above the 3, which means that 1a would be common. So if we take out the 1a, we are taking out the smallest common variable. And then we are left with 6 divided by 3 is 2, and a squared divided by a is a. We do that because we understand that every line of math must equal the one above it. So if we were to multiply 3a by 2a, we would get right back to our 6a squared. And that means when we divide 3a by itself, we will get negative 1. And again, when we expand 3a times negative 1, we get right back to the beginning, negative 3a. I'm going to do that again. So we start with 6a squared minus 3a. We're looking for the largest number and the smallest variable. And we're talking about the exponent value of that variable. So now looking at it again, the largest number is 3, and the smallest common variable is that a1. We then take our first term and divide it by our common factor. So 6 divided by 3 is 2, and a squared divided by a is a. You then take the second term, which is negative 3a, divided again by the common. 3 divided by 3 is 1. A divided by a is 1. Remember, it's a negative, so negative 3 divided by positive 3 is negative 1. On to our second example. This time we have 3 terms. In this case, when we look at the numbers first, we have 4, 8, and 6. So 2 is the largest number that's common to each. We then look at our variables, and none of them have an exponent, but we can see that q is common to each and every one of those terms. We then take each term and divide it by our common factor. So 4 divided by 2 is 2. The q's will cancel out and become 1, and you're left with 2r. 8 divided by 2 is 4. Again, the q's cancel out, and you're left with 4t. The last term, 6 divided by 2 is 3. Q's cancel out, and you're left with v. A really fast way to check if you've done your common factoring correctly is to multiply out. So 2q times 2r equals 4qr. 2q times 4t is 8qt. And 2q times 3v is 6qv. So we've done our factoring correctly. On to my last example, and here we do have some exponents. So again, first we're going to look at our numbers, 8, 6, and 4, and recognize that 2, again, is the largest number that's common to each of those terms. Now we're going to have a look at our variables. We have an x, an xy, and an xy. Notice in the first term, there is no y. So y cannot be a common factor. Fortunately, each of those terms has an x. We have a 3, a 2, and a 2. So x is common, and the smallest exponent is 2. So that becomes your common factor. And just like the last example, we take each of our terms with its sign, and we divide by the common factor that we just determined. So then it becomes 8 divided by 2 is 4, x cubed by x squared is x. Remembering that when you are dividing exponents, you're subtracting. So 3 minus 2 is 1, and we don't write the invisible 1. The second term, 6 divided by 2 is 3. The x squareds cancel out and become 1, and you're left with y squared. Last term, 4 divided by 2 is 2. The x squareds cancel out, and you're left with y. So that is a successful factor. To prove it, let's multiply out once again. So 2 times 4 is 8. X squared times x is x cubed. 2 times 3 is 6. X squared, y squared. And 2 times 2 is 4. X squared, y. So we're right back to the beginning. So again, we factored correctly. That is common factoring. And that is the actual first rule of all factoring, is to see if you can find a common factor. Now moving along to a binomial common factor. And this is the same concept as a monomial common factor. So in the last example, the last slide, we just found one item that was common to each of the terms. So looking at my first example, realize that this is one term because that's multiplied all together, and here is my second term. So hopefully you can see that the w plus 1 is common to both terms. So that is our binomial common factor. So I'm going to take it out. Just like I did on the last slide, it now becomes the common factor. And then you take your first term and you divide by your common factor. So w plus 1 divided by w plus 1 becomes 1, and you're left with 4x. Now looking at the second term, you've got 5y times the w plus 1, and if you're dividing by your common factor, you again are left with the value up front, which is 5y. And the same thing can be done here to see if you've done it correctly. So we're going to treat this as one term. And we're going to take it and we're going to multiply it by 4x. So 4x times the w plus 1. We'll do the same to the second term. And so that becomes plus 5y times w plus 1, which means we've done our binomial common factor correctly. Example number 2. You can see that a minus 2 is your common factor. You take the first term and you divide by a minus 2, and you are left with 3q. The second term, you're left with 5z. And again, when you multiply that back, you'll get right back to the beginning. Now we're on to factor by grouping. So this is a common strategy when you see 4 terms, is to group them together. It's not always the case, but most of the time. So here, we're going to group these first 2 terms together and the second 2 terms together. You look at those terms and you can see that C is common. And when you divide it out, you're left with A plus B. Now turning our attention to the second set of 2 terms, you can see that D is common, and again you're left with A plus B. So in the first set, once you take C away, you're left with A plus B. In the second set, once you take the D away, again you're left with A plus B. There's one more step to factoring by grouping, because now we're in a situation where we have a binomial common factor, and that binomial common factor is your A plus B. And just like the previous slide, you are left with the two terms in front. And there you have it, factoring by grouping. It's not always done nicely in order, so when you look at this next example, there's nothing in common if we just pair up the first two together. There's nothing in common between m and 4n squared. This would work because you have m that is the same. So I'm going to rewrite this in a way that I'm going to get two sets of terms that will have a common factor. So I'm going to rewrite it with the m squared and the 4m together, and then the negative 4n and the negative mn together. This looks a bit nicer because I can see I have m's in common, and in the second pair I have an n that's common. So I'll do that. So in the first two terms, take out the m, I'm left with m plus 4. In the second two terms, I have to make a decision here. They're both negative. I can either take out a negative n or a positive n. Now, I know that I want to try and get another common binomial factor. So I'm going to take out the negative n, and I'm going to be left with positive 4 and a positive m. So this worked out pretty well. The fact that my second bracket is the reverse of my first is okay, because 2 plus 3 is the same as 3 plus 2. So I can change that order. So I'll do that. And it's appropriate to have the variable first and the number second. So I'm just going to flip that around. And now I have a binomial common factor, which I will take out, put in front, divide it out, m minus n. So that is factoring by grouping. Sometimes you have to move them around. Factoring trinomials. Our first example, 8x squared minus 8x plus 12. When you factor, you're going to try to find two binomials, when multiplied together, gives you the trinomial you're starting with. And the method that I like to use is very consistent no matter what you see on the page. So remember, there's an invisible 1 in front of that x, and I like to use something called guess and check, which involves product, product, and sum. Remember, product means to multiply, and sum means to add. So a little side chart here, a product of 1, product of 12, and a sum of negative 8. When you're finding the product, you're finding numbers that multiply to 1, and there's only one way to make a 1, and that is 1 times 1. There's several ways to make a 12. It could be 1 times 12, 2 times 6, 3 times 4, 4 times 3, and as soon as you start to come up with the same values, but in reverse, you can stop. So those are the factors of 12. In this strategy, you're working vertically, so I'm making pairs of factors. And now I'm going to do something called guess and check. These numbers are the same, so it's going to make it a bit quicker. I'm trying to make a negative 8. 1 times 1 is 1, and 1 times 12 is 12. I can't make an 8 whether I'm adding or subtracting with a 1 and a 12. So that's not going to work. With a 2 and a 6, I can make an 8. So 1 times 2 is 2, and 1 times 6 is 6. And if I add those two values together, I will get 8. I'm trying to make a sum of negative 8. And I can still do that, because if I make those two values negative, they will indeed add up to negative 8. So the way this method now works is you place your first product numbers in the first position. So you have 1x and 1x. So that's the first done. You then take your second successful pairing and you place them in second position. In this example, the order doesn't matter because our values in the first position are both 1. So I'm going to put my 2 and 6 in place. Remember that to make this negative 8, they both had to be negative. And we're done. We've successfully factored x squared minus 8x plus 12. And the way you can check it is this. The middle term is negative 2x, and that is negative 6x. So when you add those together, it's negative 8x. The first term is x squared, and the last term is negative 2 times negative 6, which is positive 12. First term, second term, third term. Moving along to another example. I'm just going to go down here. So we've got 4x squared, negative 5xy, negative 6y squared. There's no common factor, so I'm going to use the same method. Product, product, sum. Just going to erase a little bit so that my board isn't overly populated here. And so now a product of 4, a product of 6, and a sum of negative 5. Okay, it's actually negative 6. I don't really worry too much about that until the end. I'm going to factor 4, which is 1 and 4, 2 and 2. Remember, you're making vertical pairs. So 6 is 1 and 6, 2 and 3. There are no other pairs that multiply to 6 or 4. And now we're going to guess and check. 1 times 1 is 1. 4 times 6 is 24. That won't work. I can't make a 5 with a 1 and a 24. Still working with my first pairing. 1 times 2 is 2. And 4 times 3 is 12. There's no way I'm making my 5 with a 2 and a 12. But I'm going to try the reverse and see what happens. 4 times 2 is 8, and 1 times 3 is 3. Well, with an 8 and a 3, I can make a 5. So now we'll see if it's the correct pairing. I need to make a negative 5, which means this needs to be negative 8. Negative 8 plus 3 is negative 5. So if that's the case, let's see if we can also have the other two terms make sense. So we're using our first pairing, which is 4 and 1. So 1x and 4x. Our second pairing is the 2 and the 3. Now notice that the 4 and the 2 are together. The 4 and the 2 are together. That means my 2 goes here. I'm going to use the correct tool. So my 2 goes here, which means that my 3 goes in the other position. So when you're looking at it, make sure that you pair up the numbers correctly. And the way you'll be able to tell is that when you multiply it back out, the 2 goes with the 4, there's your 8x, and your 1 goes with the 3, and there's your 3x. We've determined that 8 must be negative, which means that your 2 is your negative value, and your 3 is your positive value. So this is negative 8 plus 3, there's your negative 5. X times 4x is 4x squared, and negative 2 times 3 is negative 6. And now looking at it, I've forgotten one important detail. In this case, I have 2 variables. I have an x, y, and I did not account for that as yet. So to account for your second variable of y, make sure that the second position also has a y. And now you're done. You've factored. I have 2 more examples. And here we go. Product, product, sum. So I want numbers that multiply to 6. So that's 1 and 6, 2 and 3. I want a sum of 13. And numbers that multiply to 5, which is 1 and 5. Vertical pairs. And now we're going to guess and check. 1 times 1 and 6 times 5. Well, that makes a 1 and a 30. That will not work. Cross them. 5 and 6. That makes an 11, so I'm getting closer, but that doesn't work. So 1 and 6 is not going to be a success. 2 and 1, 3 and 5. So that gives me a 2 and a 15. I can definitely make a 13. It would have to be negative 2 plus 15 for it to work. So let's put that into our brackets. So remembering that this is your pair, your 2 and your 3. So in your first bracket, 2m, 3m. Also remember that the 2 and the 1 go together. So 2 and 1 go together, which means the 3 and the 5 also go together. There's no second variable, so there's no need to account for it. We have to have a negative 2, so this multiplication has to be negative, which makes this a negative 1 and a positive 5. So this becomes 15. This again is negative 2. Add those together to 13. And then when you multiply out your first terms, you're back to 6m squared. And multiply your last terms, and you're at negative 5. So there we go, success. One more example where I'm going to illustrate the first rule of factoring. So you can see in this example, they're all divisible by 3. So in the first slide, what we did is we common factored, and that is the rule of every factoring problem that you encounter. First, check to see if there's a common factor. So if I take the 3 out, if I common factor it, I'm left with x squared plus xy minus 6y squared. Which means I need a product of 1 and a product of negative 6. So a product of 1 and a product of negative 6. So 1 and 6, 2 and 3, and a sum of 1. Remembering that there's a 1 in front of every variable without a coefficient. I'm going to start cross multiplying. I'm trying to make a 1. I can't make a 1 with a 1 and a 6. It won't work. Can I make a 1 with a 2 and a 3? I certainly can. So your brackets will have the pair of x and 2 and 3. So we're trying to make a positive 1 and a negative 18. This gives me 2. This gives me 3. If I want a positive 1, my 2 has to be negative, and my 3 has to be positive. That will give me positive 1. And I just have to make sure that my other two terms are going to be the same. So x times x gives me x squared, so that works. And negative 2 times 3 gives me negative 6. But again, I have to account for my second variable. So make sure that you put your second variable in with the second number in each bracket. And that is factoring. The last slide now deals with special products. So when you multiply two binomials out, you get something called a special product. So if I'm multiplying, let's see here, so 2x plus 1 and 2x minus 1. That will give me 4x squared minus 2x plus 2x minus 1. These two terms cancel out and you get 4x squared minus 1. That is called a difference of squares. So we just did something called expand. And what we're going to do on this slide is contract or factor. So that is a difference of squares. And what you want to look for is the first term being a perfect square, the second term being a perfect square, and it being a difference, which in math is negative. So yes, you can use product and sum with this. The sum would be 0. So in this case, a product of 36, a product of negative 9, and a sum of 0. And you can do the same pattern that we just did in the previous slide. However, since you know it's a difference of squares, and you recognize that this pattern is how to factor it, you square root the first term, square root the second term, write it twice, and then add a plus or minus. And it doesn't matter which order you add those two signs. And there you have it, a difference of squares. Okay, I'm going to go down to my other corner here. Again, when you see two terms, check to see if it's a difference of squares. 9 is a perfect square. 16 is a perfect square. Difference is to subtract. So it is indeed a difference of squares. Take the first term, square it. Take the second term, square it. Write it twice. Brackets. Plus minus, minus plus. That doesn't matter. Just a quick refresher on what a perfect square is. 1 squared is 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. 5 squared is 25. These are all perfect squares. And when you square root them, you get back to the original number before you square. So 9 and 16 are both perfect squares. And now let's look at the other special product, which is a perfect square trinomial. So in a perfect square trinomial, the first term is a square, the last term is a perfect square, and the middle term is twice the value of the square roots of the outer two terms. This also works with a negative sign in the middle because a square root is a positive or a negative. So that's the pattern. And when you factor the pattern, you're left with a plus b, or minus, so I'm going to factor this one. That'll be a plus b squared, and if I factor the second one, it'll be a minus b squared. And just to prove that that's correct, I'll write it out the long way by writing it twice and multiplying it through. So a times a is a squared, a times b is ab, b times a is ab, and b times b is b squared. So that indeed is what I started with. And that is a perfect square trinomial. So now that you know the pattern comes from the structure of the outer two terms being perfect, and this being twice the value of the square roots of the outer two terms, you can use the factoring pattern to factor without doing product sum, which will work. But a quicker, more direct, elegant way is to simply follow the pattern. This is a perfect square. That's 1. 49 is a perfect square. 14 is twice the value of the square roots of the outer two terms. 2 times 1 times 7 is 14. So we're going to factor it. M is the square root of m squared. Square root of 49 is 7. Follow the sign, which is negative, and square it. My last example of special products, another perfect square trinomial. This is a perfect square. 25 is a perfect square. The middle term is twice the value of the square roots of the outer two terms. So I take the first term and I square it. I take the last term and I square it. I follow the sign, and I have now successfully factored another perfect square trinomial. Thanks for listening.